there, welcome to part 3 of Kinetics. So we're halfway done with the chapter. So there are a lot of problems, calculations that deal with what we're going to cover today, as well as part 2. And so I do encourage you to make sure that you're attending the Zoom lectures or that you're going back and listening to them or working through these problems, because a lot of this is going to be sort of getting in and working with that experimental data, just getting comfortable with it. Because today we're going to introduce to you a whole set of equations and how those relate together, and they're going to be based on the reaction orders. So we're building on this idea of reaction orders. Before we get there, I just wanted to review a little bit from part 2. If we think about a chemical reaction in which A, B, and C, so you have 3 reactants, reactant A, reactant B, and reactant C, to form products, and I have then I'm first order in A, second order in B, and 0 order in C. So write the rate law for this reaction. If I had A, B, and C, A plus B plus C goes to products. And remember, we don't include products in our rate law, only our reactants. And so my rate law would be A to some reaction order, M to some reaction order, and C to some reaction order. And in the directions, I tell you that A is first order. So that means that A is going to be to the first power. B is second order, and C is 0 order. So if C is 0 order, then that means that simply just falls out of the equation. So I could write it this way, or I could write the rate this way and just remove C to make it a little bit easier. Because if C is 0 order, then this is going to have no effect on the rate, and that can just come out of the equation. What happens if A is doubled? What happens to the rate? If A is doubled, since A is first order, then the rate is also going to double because these were proportional. So if A is doubled, then my rate will double. If B is doubled, what will happen to the rate? Let's say I keep A constant and I double B. B is second order, so as B doubles, B is squared, so my rate will quadruple. Let's say if C is doubled. Since C is 0 order, there'll be no effect. So my rate will stay the same. Now let's say I have a scenario where I double all 3, A, B, and C. Now what's going to happen to the rate? So this is going to double the rate. This is going to quadruple. So if I double all 3, C doesn't have any effect. This will double, this will quadruple. So my rate is going to go up by 8 times. So that's a reaction order. We're going to take this idea and we're going to expand on it in this part 3. And we're going to look at these integrated rate laws. Integrated rate laws take into account not just concentration of the reactant, but now we're going to pull back in the time component. So when we're looking directly at the rate law, we were only looking at the concentration. When we looked at the rate expression, we looked at the concentration versus time, but we treated it in a stoichiometric fashion. The integrated rate laws pull these together. So we're going to pull together time and concentration. We're going to introduce new equations called half-lives. So a half-life is going to look at the time that it takes for the concentration of a particular reactant to drop by half. That's called its half-life, and we can actually use half-lives to help us determine reaction order. And then we're going to understand how temperature affects reaction rate. So this is called Arrhenius equation. So right now we're only looking at concentration. We haven't really considered the other 2 factors that affect the rate of a reaction, which is temperature and orientation. So Arrhenius equation brings both of these to bear. We're going to be able to compare all 3 of them together. So if we look at the integrated rate laws, and I'm just going to go through this mathematical process with first order. So if I have an integrated rate law, now my integrated rate laws are going to factor in concentration and time. So I'm going to integrate these 2 components together. If I just have very simple, A goes to products. And let's assume A is first order. My rate for this would look like this at time 0. I'm going to add in a 0 there. And my rate expression, so this is my rate law, and my rate expression, since it's first order, then I can look at my rate expression this way. It's going to be proportional. over a particular amount of time. And if I set these two equal to each other, then it looks like this. A first order equals the change in A over the change in time. I'm going to integrate that to get to here. ln A at some time t over A at 0 equals negative kt. I'm going to tell you what all these things are. So there's a whole sort of series of steps that you can go through to get there, and if you want to see them, your book walks you through them. They kind of look like this. So if you want to see the whole nitty gritty, I would say go to your book and look at it as opposed to my chicken scratch here. But yeah, you see, this is where you're going to do your integration, and then you'll get to your integrated rate law. But you guys don't have to do that. You just have to know the laws. So this is the integrated rate law for first order. And if I write that out, I could write it this way, or I could write it this way. ln A t equals negative kt plus ln A0. Kind of ran out of room on my paper there. All right, so this is the concentration of reactant A at time t. We're integrating concentration and time. This is my rate constant here. This is my time. So whatever this concentration is, this is the time that it's at. And this is my initial concentration at time 0, so the beginning of that reaction. So this is the integrated rate law. So I have two concentration values. I have my concentration right before the chemical reaction is to occur, and my concentration at some amount of time that has elapsed, time t. So this would be my concentration at time t, and this would be actually time t, and this is my rate constant. So this t here just denotes this. It's not, you're not actually multiplying by that t. Just denotes that is the concentration that's happening at that time. If I plot this, so this is first order. So this is my integrated rate law for first order reaction. If I plot this, this is what it looks like. ln of A at time t versus time t. And what that looks like is it's going to give you a graph that looks like this. The slope of this graph is equal to the negative of the rate constant. The y-intercept here is ln at A0. Oops. So this is natural log. This would be the graph of this. And we graph it because this is going to allow us to determine the rate constant. So oftentimes what we're doing is we can measure the change in concentration over a function of time, but we don't really know anything about the rate constant, and maybe we want to calculate the rate. We need to also calculate the rate constant. This is going to allow us to do this. All right, so I'm going to rewrite my first order equation here, my integrated rate law. I'm going to write it this way because this format, that is going to give me a straight line. So y equals mx plus b. So my y-axis would be ln of A at varying concentrations depending upon the time. This is going to be the time. The slope is going to give me the rate constant, and b is going to give me my y-intercept. So oftentimes we'll graph these to get this slope here, which is going to give you the rate constant. So this graph of this would look like this. This would be ln of A at time t. This would be t. My graph's going to look like this. I'm going to have a negative slope, so my slope equals negative k, which makes k constant. So k is always going to be positive. So if I have a negative slope, the negative of that negative slope is going to give me positive. So k is always a positive value. Rate is always a positive value. So just something to keep in the back of your mind. So k and rate are always going to be positive. So if I have a negative slope in my integrated rate law, I'm taking the negative of that rate constant. That's first order. If we look at second order looks like this. My integrated rate law for second order is going to be different. It's going to look like this. Now remember, my rate law would look like this for a second order. My integrated rate law, when I integrate it, it's going to look like this. 1 over A to that time t. Now I have a positive rate constant times whatever time t is, plus 1 over A0. So this is my y-intercept. I still have this y equals mx plus b, but now my slope is positive. So when I graph this, I should get a positive slope. And you do. Graph of this looks like this. So now I'm graphing 1 over the concentration of A at time t versus t. And I'm going to get a graph that looks like this. And so my slope here is just equal to the rate constant. And then this is my y-intercept, which is 1 over A at time 0. Now, zero order is the third one that we've talked about. So zero order is probably the simplest one. Zero order, remember, my rate law is k times a to the 0. So my integrated rate law for this is going to look like this. A at time t equals negative kt plus a at time 0. So this is still written as y equals mx plus b, but now my slope, I'm going to have a negative slope again, and my slope is going to give me that rate constant. So in all three of these, when I graph these, I'm graphing them to get that rate constant, and this is going to have a negative slope, so it's going to look like this. And here I'm just graphing a at times t versus, and my y-intercept up here is a0. So that's the integrated rate laws. So another way to tell if you have first order, second order, or zero order is to do all three of these graphs with your data, and whichever one fits the best fit straight line is going to tell you what the order is of your reaction. All right, here's a table out of your textbook. And in this table, what you see is that here I have my order is in this first column, 0, 1, or 2. Here's my rate law, so that original rate law expression. Here are my units of K. So you see my units of K are going to be different depending upon the reaction order for A. And this is our very simple view where I only have one reactant. Now I have my integrated rate laws, and I have them written in the y equals mx plus b format. And then here would be your straight line plot. And now we have something called half-lives. And so half-life is the amount of time that it takes for your concentration of your reactant to drop by half. So here, if I look at this data here, and I want to think about half-lives, if this is my initial concentration of my reactant AB, I might look down here and see if I can find something where that has dropped by half. This would be close. It would be roughly half. I might find something better. So I might compare this point to this point, and that would give me, because this is almost dropping by half, maybe the 0.302 to the 0.149, that's where I've had a drop in about half of my concentration. So I would look at the difference in time for that, and that's your half-life. So it's concentration to drop by half. And you can use this to determine reaction orders. And so I'm going to go through the 3 half-lives with you. So remember, we're only looking at 0, 1, and 2 in terms of reaction orders. So each one is going to have a different half-life. If I have a first order reaction, my half-life for that is going to look like this. T1 half, this indicates half-life, 0.693 divided by K. So this is my half-life. This is my rate constant. And what you see here is that there's no concentration of my reactant in here. So there's no reactant concentration in my half-life. And that's important because that means that the half-life is going to be constant throughout the entire reactions. It is the half-life, T1 half, is independent of the concentration, and it's going to stay the same throughout the chemical reaction. If I have a scenario where I have time and concentration, and I see that it takes the same amount of time to drop the concentration by half anywhere that I'm looking in my data, then that's going to tell me I'm first order. If I have second order, my half-life, I told you guys there was a lot of equations in here. My half-life here is going to be this equation here for second order. T1 half equals 1 over rate constant times A. And this is where we're looking at my initial concentration. So this is my rate constant, and this is my concentration of A at time 0. And this is my half-life. If I have a 0 order, my half-life looks like this. T1 half equals my initial concentration over 2 times my rate constant. and this is concentration of A at 0. First order, I don't have my reaction concentration in that equation, and so the half-life is going to be independent of the concentration, but I have concentration in both of these. So my half-life is going to be affected as the concentration of my reactant drops. So here, as my concentration decreases, as that reaction proceeds, this is going to get smaller and smaller and smaller. So what is that going to do to the half-life of this equation? For second order, as my concentration of my reactant decreases over time, my T1 half is going to get longer. If I compare several different half-lives, I'm going to see a change in my half-life here. It's going to go maybe from 60 seconds to drop by half to 100 seconds to 120 seconds. That's going to tell me that this reaction order is second order. Here, because my concentration is in the numerator, as the concentration of my reactant decreases over time, as that reaction proceeds, my T1 half is going to get shorter. That's going to tell me that it's going to take less and less time for the concentration to deplete by half. So as this gets smaller, this is going to get smaller because these are directly related. So to find my reaction order, I can do my initial rates method. If I have rates and I have concentrations, I can look at a graphical analysis, so I can graph them all and see which one is going to give me a straight line, or I can compare half-lives. And so both of those are going to give me an idea of the reaction order of that particular reactant in the reaction. And right now we're only looking at reactions that have one reactant. So I'm going to go back to that data that I just showed you. So here, if I look at this data and I want to determine the reaction order, I'm going to pick multiple points here where my concentration is dropping by half. So I might take this first one, 0.95, and half of that would be about 0.47. This is close. It's not great. It doesn't have to be exact, but it's close. So the difference in here to here is 50 seconds. So that's my first half-life data point. Now I'm going to pick two more, so maybe I'll do the 0.302 and the 0.149 because that's closer to 1/2, right? So here, if I look at the difference in time that happens between this dropping by half, I see I have 100 and 100 and 250. So my difference here for this 0.302 to drop by half is 150 seconds, whereas up here it was 50 seconds. So my half-life is getting longer and longer as the reaction proceeds. If I take 0.225 and if I drop that by half, I'm going to be about right here. I see this is going to drop by 100 and 200 seconds, right? So my half-life is getting longer and longer and longer. So that tells me that this is probably second order with respect to my reactant because my half-life is getting longer and longer as I compare points along through here. If there was no change, then that would tell me it was first order, and if it was getting shorter, then it would be zero order. So I can look at my half-life and determine something about the reaction order as well. Now we're going to look at the effect of temperature on rate. So what's happening, because up to this point we haven't considered temperature at all on the overall rate of a chemical reaction. So now we're going to look at the effect of temperature. And so if you remember, the three things that affect the rate of a reaction are concentration, which we've dealt a lot with up to this point, temperature, which we haven't talked about, and orientation. So we're going to look at temperature and we're also going to look at orientation. We're going to look at those together. And we're going to do that using this equation here. It's called the Arrhenius equation, and it counts for the effect of temperature on rate. And also orientation is kind of couched into this frequency factor. So this is the equation here. It looks like there's a lot going on here, but there isn't. It's not too bad. All right, so K is our rate constant. So this Arrhenius equation looks like this. I have big E, big A here. I have an exponential here. Lots of new terms in here. So let's pick these off one by one. This is my rate constant, the same little K we've been dealing with this whole chapter. This is an exponential. R is my ideal gas constant, but it's in units of energy. It is 8.314 joules per mole K. So that's my value for R. T is my temperature in Kelvin. So when I multiply T times R, my kelvins are going to cancel out and I'll be left with joules per mole. My EA is a new term. This is called the activation energy. And then this big A here is called the frequency factor. So those are components of the Arrhenius equation. This whole thing here is often called the exponential factor. So what is activation energy? So let's look at EA first. And this is the energy that needs to be overcome for a reaction to happen. And we haven't really looked at this before. We've talked about the things that affect a chemical reaction. We've looked at the heat of a reaction, but we haven't really considered activation energy because activation energy is hard to measure. We usually measure it experimentally, but it affects the rate. So the larger your activation energy, the slower the rate, because that means there's more energy that's going to be required for that reaction to happen. Let's just consider a simple reaction. Let's say I have hydrogen gas reacting with oxygen gas to produce water. I'm going to draw this on an energy scale where we have reactants and products. So my reactants are up here and my products are down here. And if you remember from the last chapter, when we look at this, this is the change here from my products to where my reactants are on my energy scale is my heat of the reaction. In this case, since my products have less energy than my reactants, this is going to be exothermic. And delta H of the reaction is negative. We'll come back to this thought when we get into thermochemistry. What we're not considering here is the activation energy. How much energy, it doesn't just, chemical reactions don't just go this way. There's something that has to happen. You have to put energy in and then you get energy out. That's the activation energy. So this is the energy here that I'm going to have to put in. Once I get over this hump, then it's smooth sailing until I get down to my products. So the higher this is here compared to here, if my activation energy is up here, this is going to be a much faster reaction than something that had a higher activation energy. If I had a lower activation energy, that's going to be a faster reaction. So the lower this is, the faster the reaction. And this can be affected by temperature. So if I add in temperature to this, then I'm going to affect that activation energy. So activation energy can be lowered by just increasing the temperature of the reaction. So let's talk about A, frequency factor. It's kind of a catch-all. So it catches in there the number of approaches. Remember, we're talking about collision theory here. So the number of approaches to the activation barrier, that's this guy here, this activation barrier, per unit of time. So how many times do the reactants collide and approach this activation energy here? So you can have many, many collisions, but if they don't have enough energy to get over this activation energy, then the reaction isn't going to occur. So the frequency factor kind of takes that into account. It takes into account the number of approaches and also how successful they are. So all that's going to be in that frequency factor. The other thing, I don't want to spend too much time on the frequency factor. The other thing that I will say is that it also takes into account orientation. So I could break A up, and your book goes into this in much more detail, but there's a lot going on in this chapter. And so of all the things I want you to focus on, probably the frequency factor is the least of them all. But just to say that the frequency factor is this culmination. It has these two things. Remember, it's how many attempts per unit of time, and it contains both of these things. So the first one is called Z, which is the collision frequency. So how many times, the number of collisions per time. How many times are those things colliding? As Z goes up, then you're going to have more opportunity to have a successful collision. P is your orientation factor. And this is where if you have an orientation requirement, this is where it's going to start to slow down the rate of that chemical reaction, because as the orientation factor, as you have a constriction on the orientation to have a successful chemical reaction occur, then this value is going to weight heavily on your frequency factor here. And so this couches both of these. How many collisions, and is there an orientation? And so all that is inherently built into A when A goes into the Arrhenius equation. And that's really all I want to focus on in terms of the frequency factor. And your book goes into it a lot more, but like I said, and of all the things in this chapter, that's probably the least important one for you to focus on right now. The Arrhenius equation allows us to determine the activation energy. And we do this through graphical analysis. And that looks like this equation here. ln of k equals negative EA over R, RT, plus ln of A. So this is my y equals mx plus b format. Y is my natural log of the rate constant. X is 1 over the temperature in Kelvin. And then the slope of this is going to be, I have a negative slope. The slope of this is the activation energy divided by R, and R is a constant. So activation energy is always going to be positive. The slope gives you a negative slope, so you're going to take the negative of the negative of the negative, and that's going to give you EA divided by R. So to get EA, you're going to take the slope and multiply it by R. And remember, your slope is going to have a negative value. So a negative of a negative is a positive, so you take the slope, multiply it by R, that's going to give you your activation energy. So you would use this graphical analysis if you had multiple runs of a reaction at different temperatures. I would do my reaction, my chemical reaction at different temperatures, and then at each of those temperatures I would have a specific rate constant. So I'd run it multiple runs of reaction at different temperatures. I would calculate K for each temperature, and then I would plot to get my activation energy. So there's 3 things you have to do before you get to the activation energy. I'm going to do this reaction several different ways. I'm going to be able to measure the rate constant however it is that I can. And then I'm going to plot the natural log of the rate constant for each of those runs as 1 over the temperature. So if I had 3 runs and I had 3 data points on here, I would have different K values depending upon the temperature that they were run at. Then I would plot to get EA using the slope of my straight line. If I was able to do multiple runs of a reaction, this would be the best way to get your activation energy, because by taking the best fit line to this, then you're reducing your amount of error that you would get from viewing between individual data points. If I only had 2 data points, meaning K values at only 2 temperatures, it wouldn't make sense really to do this plot for only 2 data points. So really you would want to do this if you had 3 or more data points. If I only had 2, I could use this equation here. Because remember, I'm going to have 2 different rate constants, EA over R, 1 over T1 minus 1 over T2. So if I have run 1, then I'm going to have rate constant 1 at temperature 1, and then I'll have run 2 at rate constant 2 at temperature 2. So I could plug them into here and solve for EA this way. This is not as good as doing your graphical analysis, but if you only have 2 data points, then there's no reason to graph them. You could just use this equation here because this is the slope here. All right, so that ends part 3. And we will come together for the last part of this chapter in our next video.